Vanakkam. Welcome to this video on biomechanics. We have been looking at shoulder joint and muscles responsible for movements in shoulder. In this video, we will be focusing on solving a couple of simple problems in statics in the shoulder joint. Consider this situation. It's a scary looking problem, but we'll take step by step and try and solve this. Consider the situation. A person is holding a 5.2 kg sphere in his hand. Okay. So, the weight of this is 9.81 times 5.2. The mass is 5.2 kilograms. The hand is holding this and the arm itself is completely horizontal. The arm is completely horizontal. Arm held horizontally as shown in the figure. The muscle responsible for producing the force to overcome this load and the arm being held in horizontal position is the deltoid muscle. So, a tensile force in the deltoid muscle stops the arm from rotating about the shoulder joint, okay, from here at this point. This is the shoulder joint. If there was no force produced by the deltoid muscle because of the mass of the upper arm and forearm and hand and the load in the hand, there is a tendency for the whole thing to rotate like this, but that does not happen. That means that this deltoid muscle is producing a non-zero force to keep this whole thing or the whole arm in static equilibrium. Okay. This force is acting at an angle of 21 degrees, it is shown here the value as shown in the figure, 21 degrees. The question is, find the force exerted by the deltoid muscle. We need to know what is the deltoid muscle force. What is the force that is produced by the deltoid muscle? Some more details are given. We cannot assume that the upper arm and forearm are massless. They have mass, okay, and their corresponding centers of gravity or center of mass are given. So, the center of mass of the upper arm is at a distance of 132 mm and the mass is given to be 2.1 kg. The center of mass of the forearm is given to be at 410 mm from the point O and that mass is 1.5 kg. The mass of the hand itself is 0.5 kg and its center of mass is at a distance of 640 mm from the point O. Okay. And we can assume that the external mass of 5.2 kg is also acting along the center of mass of the hand. So, both are aligned. In other words, you are keeping this sphere exactly at the aligned with the center of mass of your hand, something like this. Okay. Now, the question is, given that these are all the forces that are acting and these are the distances at which this is acting, and I know that the deltoid muscle is inserting at a distance of 123 mm from the joint and its force is acting at an angle of 21 degrees to the horizontal, can you tell what is the force that is produced by the deltoid muscle? This is all we need to know. Okay. Before we get into the analysis, let us try and get an idea of the total mass of this system that is being overcome by the muscle. Let us just add all these masses. This is not the solution. I am just trying to get an idea of the total force, right, or the total mass. 2.1 1.5, 0.5, 5.2. Let's add this. So, that would be 9.3 kg. They are all not acting at the same point, I understand that. So, they are all not acting, they are not having a, or at least we do not know the center of mass of this whole system. So, that is not the point. Roughly I am trying to understand what must be the total force that must be produced if they were all acting along the same idea. So, I am trying to develop an intuitive or a ballpark figure in my head. This is critical because sometimes students find this answer and then they will write out the answer as 9.3 Newton. They might get some answer, we do not know, they might get some answer, say not necessarily 9.3, they might get some 12.6 Newton. It is extremely unlikely for this to be correct. Why is that? Because the scales with which you are operating and the angle with which you are operating, it is very unlikely for this answer to be correct. So, we need to develop this intuitive or back of the envelope calculation mindset before we solve problems, but this is not the rigorous way of solving the problem. I am just trying to see what is the approximate order, the scale in which the solution is expected to be, and that is not in the order of units of Newton, it is definitely in hundreds of Newtons. That is my expectation, but let us see, let us try to solve this, okay. Or perhaps it may even be in thousands of Newtons, but not many thousands of Newtons. It is going to be in the high hundreds of Newtons because of the way this muscle is attaching, but let us try and solve this problem. So, here in this slide we present the situation, and I have modeled this whole arm as a bar that can rotate about the point O, but cannot translate along the x axis or y axis for these xy axis that are shown. That means that there will be a reaction force OX along the x axis and a reaction force OY along the y axis, because this bar cannot accelerate in the x or y direction, but it can rotate. At point A is where the muscle attaches, and its force is acting at an angle of 21 degrees, and the force produced by this muscle I am calling as Fm. This is what I do not know, this is what I am interested in finding, okay. And that distance is 123 mm, okay. At point B, the weight of the upper arm is acting, that is 2.1 kg, and that distance is 132 mm, okay. And at point C, the weight of the forearm or the lower arm is acting, and its mass is 1.5 kg, and that distance is 410 mm. And the hand and the external mass together is 5.7 kg. How did I get this? Because the external mass itself is 5.2 kg, the hand is shown to be or known to be having a mass of 0.5 kg. I am adding the two and I am getting that mass as 5.7 kg, and it is acting at a distance of 640 mm, right. So, we are interested in finding Fm, right. So, let us write out the equations of static equilibrium that we have seen previously in our introduction videos on engineering mechanics. In this case, sigma fx equal to 0, sigma fy equal to 0 and sigma m equal to 0. Counterclockwise considered positive, this considered positive, this considered positive, right. These are the equations that we are interested in solving. It seems like before we go out and write out the force equations, and because the question only states find the force Fm, and it is not asking me to find the two other unknowns Ox and Oy, although it would be instructive to try and find those. Let us start by finding a way to find the force Fm. It seems to me like that is not something that I can find by merely solving the force equations. Sigma fx equal to 0 and sigma fy equal to 0 alone may not give me this. Why do I have this feeling? Because Fm is not along x axis or y axis, it is inclined. So, that means it will have both an x component and a y component, and because there are two other unknowns Ox and Oy each acting respectively in the x and y direction, I will have two equations and two unknowns if I solve fx and or x component of Fm and y component of Fm and Ox and Oy essentially. So, there will be many unknowns. I will anyway have to write out the moment equation, and in the moment equation, if I take the moment about O, which is reasonable point to take the moment about, then there will only be one unknown because all other distances and forces are known to me. So, it is likely that I will simplify this problem by writing out the moment equation and expanding it, in which case I will have only one variable and one equation, and it will be a simple solution, except of course bookkeeping is a problem because there are many forces and many distances that are involved. You need to be very cautious about how this is being done. So, if you are carefully doing this and if you are keeping the books clean, it is very likely that you will be successful in solving this, right. So, let us write out let us write out the moment equation, which is sigma m about the point O counterclockwise considered positive is 0. That is the equation that I am attempting to write, right. Now, let us look at this force Fm itself. Fm is acting at an angle of 21 degrees. Its magnitude is what I am interested in finding. It will have a vertical component and a horizontal component. The y component will be along the positive y axis and the horizontal component will be along the negative x axis, something to remember, okay. And what will be the, I am going to call this as some Fmx, right. That would be Fm cos 21 degrees, is it not? And Fmy would be Fm sin 21 degrees. Note that I have not actually included the SIGN sign for this, okay. So, when I am writing out in the actual equation, or let me write out that, okay. So, this will be minus this in the, okay, or rather if the arrow was pointed like this, then Fmx If the arrow was pointed like this, then Fmx would be minus Fm times cos 21. Okay. Now, let us write out the moment equation and try to solve this. What are all the various things that are there? Let us count the number of forces. There are two components of force from Fm, one from the weight of the upper arm, one from the weight of the forearm, and one from the weight of the hand plus the external mass. Okay. So, there are essentially 5 with 5 different distances, except that one of this Fm and its components will have the same momentum. Will they? Perhaps not, right, because only one of these components will have that momentum. Okay. Something to keep in mind. Let us try and write this out so that it is a bit clear for us. A question that comes is, will the x component of this have a moment? Will this cause a moment? That is a question that we will have to come to, but for completeness it makes sense for me to write this out. I know that immediately because this x component is acting along O, it will probably not cause this. In this case it is shown to be acting along O, but that need not be the case. Maybe the joint is here and the muscle is attaching at some distance from the joint along the y axis. In that case, the moment arm will exist for the x component of the force. So, it makes sense to completely write out this equation, okay, not just write the y component. Let us not assume that, because this is the first problem that we are solving. Let us, for completeness, it makes sense to write out the entire equation. So, I will start out by writing Fm sin 21 times 123 by 1000. Why is that? Or rather 0.123, 123 mm times 0.123. What is this? This is 123 mm expressed in its SI units, okay, which is meters. So, 0.123 minus, will this be a positive moment or a negative moment? Well, because Fmy is acting in this direction and the joint is here, it will be a counterclockwise moment, which is positive. So, Fm sin 21 times 0.123 is positive, minus 2.1 into 9.81. 2.1 is the mass, okay, into 9.81 is the acceleration due to gravity. Always assume acceleration due to gravity is 9.81. Kindly avoid assuming acceleration due to gravity as 10. Okay. It is not a matter of convenience. In your actual problems, I will expect you to assume g to be 9.81 meter per second squared. Okay. 9.81. Are we done? No, because we will have to write out the corresponding momentum, and that momentum is 132 mm. So, I am putting a 0.132. Yes. I have written negative in this. Is that correct? Yes, because this force is acting downward and this is where the joint is. It will cause a clockwise moment. It will cause a clockwise moment like this, and because of this reason it will be negative, because I am considering counterclockwise to be considered positive. Okay. Again minus 1.5 times 9.81 times, what is this distance? 0.41. Okay. Minus 5.7 into 9.81 times 0.640. This is the entire equation, but we are not done yet. I said we will also write out the x component. What is this x component? X component is Fm cos 21, is it not? If there was, that would be minus Fm cos 21, but it is acting along the x axis. This component is acting along the x axis. It is not having a momentum, right? Because of that reason, this will become 0. The momentum would be 0. Okay, and this whole thing sums to 0. Okay, I am not doing the numerical. I request you to try and solve for Fm. This is a single equation in one variable. You will only have to simplify this equation, and when you simplify this equation, you will find, and there is no Fm cos 21. This becomes, the whole thing is 0, right? This whole thing is 0. Fm cos 21 is 0, as in that term, Fm cos 21 times 0, that term is 0, right? If you get that, you will find after some simplification, Fm is actually 1010.44 newtons or 438 newtons. Let us go back and take a look at the situation. To hold a mass of 5.2 kg, the deltoid muscle is producing a force of 1000 newtons, or 5.2 kg, say even at g equal to 10, 5.2 kg is about 52, let us say 50 newtons. For 50 newtons to be overcome, the muscle will have to produce 1000 newtons. Of course, there are other masses that I have not discussed. There is the mass of the upper limb, there is mass of the upper arm, there is mass of the lower arm, there is mass of the hand. All these things considered, even if you add all of them, I said it is about 9.x, right? We in the previous slide we saw it is about 9.3. Even if you say it is about 90 newtons, for example, for the sake of discussion, the muscle produces about 10 times as much force. Why is this? Why does the muscle have to produce a force that is 10 times as much as the force that is produced or the weight of the entire arm? That does not make much sense. Why is this? Because there are several things at play here. One is, the muscle is attaching at a small momentum, whereas the external load is acting at a very large momentum. The muscle is acting here at 123 mm, right, whereas the external load is acting at 640 mm, very large. But not just that, only the vertical component can overcome this, and it would be helpful if the muscle is acting entirely along the y axis. But that is not what is happening, because the component of force that is going to overcome this is the y component, and Fm sin 21 is a much smaller number than Fm sin 90, right. So, the angle of attachment of the muscle is small, because sin 0 is 0 and sin 90 is 1. 21 is closer to 0 than 90, right. From this I know that it is attaching at an inconvenient angle, slightly less, much less actually, not slightly less, at a much lesser angle than what can be a very convenient solution. Although we look at this from these points of view, what actually happens is there is a need for evolution to produce these kinds of forces to overcome these loads. So, this is the reality for the human musculoskeletal system in many cases, not always, in many cases. Okay. Now, what is also not known but not asked in the problem is what is OX and what is OY. This is not asked, but I request you to go back and write out sigma fx equal to 0 and sigma fy equal to 0. Now that we know Fm, right, now that we know Fm, the x component of Fm and the y component of Fm is also something that we know, because I wrote that the y component of Fm is Fm sin 21, x component of Fm is Fm cos 21, and so I can write out the sigma fx equal to 0, sigma fy equal to 0, including Ox and Oy, and solve for this and try and find the values of Ox and Oy, because each of them will be one equation in one variable. The other variable that will be there is Fmx and Fmy, but we know Fm, so you can compute that. After that, you will find Ox and Oy to be respectively 943.325 newtons and Oy to be minus 270.875 newtons. That means Oy is minus in the given y direction. So, it is acting downward like that. Okay, something to remember. So, these reaction forces, please do take a few seconds, few minutes to solve for these reaction forces using sigma fx equal to 0 and sigma fy equal to 0. So, with this we come to the end of this video on a simple problem. We will continue our discussion on simple problems on shoulders or upper limb in the next videos. Thank you very much for your attention.